Okay, so this is industrial cybersecurity from the perspective of the power sector today. Quickly, introductions. I'm Wade Polk. We got Jay Novak here and Paul Malkewicz over there. We're all control systems engineers. We design the brains of power plants, mining facilities, etc. Our company is Worley Parsons. We got 29,000 employees in 40 different countries. We do everything from infrastructure to environment to power, mining, minerals, hydrocarbons, and even some manufacturing. Okay, so what kind of stuff can you expect today? You learn a little bit about what has happened, what can happen. You'll learn a little bit about traditional process design as well as malicious process design, something fairly new. You'll learn the basics of protecting a power plant, and then we'll give a case study of a PLC. The security flaws and how to mitigate those security flaws. You'll see examples of worst case scenarios, and after the talk we'll give an audience free-for-all where you'll all have the opportunity to attempt to hack our network. In doing all this, you'll get an indirect overview of process design and controls. What not to expect: we won't be discussing industrial cybersecurity in depth. We wrote a pretty large 70-page paper on that. You won't learn how to be an INC engineer. That takes about 6 years. We won't talk about network hacking in depth either. Okay, so what is an INC engineer? We design, we specify, and we purchase instrumentation, controls, controllers, and network equipment. We develop, test, and evaluate control logic and programs, operations maintenance procedures, and system and network designs. We also are required to meet various regulatory requirements, such as NERC, NRC, which we'll talk about later. Thank you.
So, what is a control systems? I mean, I think my first introduction to control system was through a cartoon like Homer Simpson, where he's sitting at his control table and twisting levers and pushing buttons and turning on the parts that are sitting, turning them off. But in reality, control system is quite a bit different and complicated. Control system is a set of instruments, controls, and controllers used to manage and control the behavior of process machinery and thus the process. First thing on the list we have is instruments. These are variable devices that collect and transmit data. They can be for flow, temperature, pressure, vibration, etc. What they do is usually via either hardwired IOs or analog IOs, or maybe some kind of proprietary communication that transfer data back to the individual controllers. As far as controllers goes, they modify the operation of machinery or the process. Some examples of this are actually buttons and levers and switches. Other ones are more involved, like HMIs, human-machine interfaces, and etc. Now we're going to move down to controllers. SCADA, you guys have like 6 or 7 speeches on SCADA this past few days, so we're not going to get far into that. DCS, distributed control system, basically a set of modules and controllers spread out throughout the plant in the different locations that vary the process of the plant. Then you have things called PLCs, programmable logic controllers, and these devices are actually earlier they were fairly simple and they were used to work a simple process. But now they're getting more robust, they're getting more developed, they're getting bigger. They're trying to catch up to the DCS portion, but they're not there yet. Then we got smaller controllers, such as single loop controllers, SLCs, for small applications. So basically, all this I/O and all these controllers do one function. They energize, turn on, actuate devices like motors, valves, pumps, and actuators. Go ahead, go to. Well, thank you. In terms of magnitude, a typical 2 gigawatt power plant has upwards of 150 PCs, around 50 PLCs, 1 to 10 DCS loops, and hundreds of HMIs. Again, the complexity and the size depends on complexity and the size of the plant. The more units, the more environmental controls you have, the more things you have running in the plant, the more complex the plant's going to be. So what are some roles and responsibilities? We basically have 5 groups within a plant. First, we have engineering, and that's us. We design, build, and buy the equipment. That's what engineers do. Next, we have operations, and operations basically run the plant. They're maintenance. They're at the plant 24 hours a day. They make sure everything works. And next we have the IT, and IT's they handle enterprise management, hardening, running of the computers, etc. And last group is management. I really don't know what management does. I'm kidding. They give the money, they give the budget and the schedule. We need those guys. We really need those guys. But if you can notice, one more please. And also we have the auditors, which are people that eventually will come in and do very bad things to us. But if you can look at the network right here, you can notice there's a connect between engineering and operations. Basically, that's a kind of a marriage of convenience. They have to talk to each other. They have to communicate with each other, because if they don't, your power's going to go off. That's simple as that. IT is a little bit separate on the side. They don't know much about control systems. They know a lot about network diagrams, but they don't know what to do at control. They don't know how to control a process. So if we go into ideal roles and responsibilities, we can see that all the three factions, or actually all the four factions, are kind of merged together. By this we mean that engineering will provide the design, the specifications, IT will update the patches, and the operations will keep the plant running. But all three factions have to work and have to cooperate with each other in order to have a safe, robust plant. I'm going to go ahead. And also, I forgot to say, management has to give the money and give us long enough of schedules to do what we need to do. So what's the worst that can happen? I'm going to let Paul talk about that.
All right, so what is the worst that can happen? And there have been a lot of talks today. How many people, just out of curiosity, went to James Arlen's talk this afternoon about cyber douchery, something like that? Yeah. He talked a lot about this, about what the worst case scenarios are. Essentially, there's two different viewpoints on this, and everyone falls within somewhere between these two. You have the really optimistic viewpoint that says, well, nothing's happened so far, there's nothing broken, so why spend a lot of time and money trying to fix it? The industry, especially in the power sector, is sort of missing a catastrophic event that's happened that you can point to and say, well, if you don't secure your network, this is what's going to happen to you. It's going to cause this much money and this much damage, so that's why it's important to do this stuff. It's like you can't see the problem, so there's no problem there. It reminds me of a story. It might be a joke. I can't remember. When you talk about this stuff, they kind of get blurred together. About I think it was a military installation that they were running a network. They wanted to install there an intrusion detection system. So they put it into place. They turned it on, and immediately they saw all kinds of unauthorized activity on their network. And so they go to the person running the installation, a general or something, and they tell him what happened. And instantly the general gets angry at them and starts yelling at them and says, why'd you guys put this thing in? Before, we didn't have any problem. There was no one trying to attack our network, and now there's all kinds of people trying to attack our network. So that's the kind of problem we have, is that you can't see the problem because nothing has really happened serious, so you can't point to that. One of the other things that these people will tell you is that these plants are they're intrinsically safe, because when you build a power plant, you're putting in all kinds of redundant safeties, mechanical interlocks, things that even if someone was able to get complete control of your network and start turning things off and turning things on and screwing things up, these safeties are going to kick in and prevent pressures from building up and prevent things from really bad from happening, prevent the most catastrophic types of damages. On the other side of the scale, you have the pessimistic view, which is that the IT person who is preaching fire and brimstone up on the stage, telling you that if you don't secure your control system network, PLC is going to come to life and drive to your house and punch your kids and drink all your beer at night, which you also don't want. And there's some truth to that too, because power plants are typically they're extremely complex. They've a lot of times just have giant piles of explosive materials lying around in the yard, specifically at coal plants, and they're things that need to be protected. So you've got to realize that there's a lot of dangers inherent in running one of these things. In addition to that, they're often really, really old, especially with power plants. Some of these have been running for 30, 40, 50 years maybe. Which means that a lot of the original equipment is in there that's 30, 40, 50 years old. A lot of the original control systems in there are also that old. And then as things get upgraded, you get a patchwork of different types of controls from different ages, and that's what causes a lot of the vulnerabilities that you see out there now. In addition to that, because you don't have the original design in there, a lot of the safeties that you've built into the plant, maybe they're not going to function like you expect them to when you need them to. You have a pressure building up in a tank somewhere, and you expect one of your pressure relief valves to open up, and it hasn't been maintained in 20 years, or it's been taken out because somebody didn't think you need it, and you no longer have that safety. So I talked just a few minutes ago about what the worst case, what's happened in the industry so far, and like I said, there haven't been a lot of things that you can point to and say, that's a really bad thing that's happened, and that's why we need to fix our system now. There have been a few things that have happened. I guess you can call them near misses because nothing terrible has come out of them. But for the most part, there's nothing to point to. I'm just going to go over, we picked out a small cross-section of things that have happened. There's things in the news even recently that are happening with control systems in SCADA, but just a few up here. One of them in 1999, a petroleum gasoline pipeline up in Washington State was building. There was some pressure building up. It was all due to non-control system related things, unrelated incidents. The pipeline was damaged, and so you had some structural weakness there. And as a result, it exploded and spilled a bunch of gas into a nearby river, and that lit on fire, and it killed a few people. Like I said, that's not there wasn't a cyber attack involved there. There was no control system problem involved there. Unfortunately, what happened at the same time, completely independently, is there was a contractor or someone working on that system as this was happening. Whatever they were doing, for whatever reason, caused the control system to freeze up, become unresponsive. So where there'd normally be procedures, the operator of the pipeline would have seen that pressure build. They would have been able to do something, take some type of action to relieve the pressure. They weren't able to do that. So, I mean, that's not a cyber attack, but that's the type of thing that can happen when you don't have, when your control system isn't operating the way it needs to be. In addition to that, just another example of an untargeted attack, something that can happen without someone specifically going after you. In 2003, in a nuclear plant in Ohio, the slammer virus was able to make its way onto a control network through, I think, an unsecured contractor connection. As a result, the plant wasn't operating at the time, which is important. If it was an operating plant, this would have been much, much worse. It wasn't operating, and since there was so much additional network traffic due to that virus, the safety monitoring systems, the computers that monitor all the safety equipment, weren't able to communicate with the rest of the plant, which is a terrible situation to have in a nuke plant especially. Like I said, there's a lot of others, but it's hard to point to one in particular that has a devastating effect. All right, next we want to talk about some root causes. The first thing that I want to say is there's a lot of root causes, all right? There have been 5 or 6 talks about SCADA and cybersecurity and all that stuff at industrial plants, and I'm sure every one of them is going to point to a different list of causes and a different list of problems, and they're all right to some extent. The ones we want to talk to you guys about are the ones that are important to us as controls engineers, and that's the design of the plant, so the stuff that happens before the plant is even running. Right now, a lot of the focus on security is on the IT side, the side of hardening your computers and which software you install and where do you put your firewalls and that type of stuff, which is all really important stuff, and that's where the focus should be, but you miss the boat a little if that's all you focus on. The thing that's important is that you need to start the process earlier. When you're purchasing equipment, when you're specifying equipment, you need to specify stuff that's intrinsically safe to put on a network. If you're buying stuff that's not safe and is just automatically is dangerous off the bat and has all kinds of flaws, you're creating a whole lot of work for the people that need to make that secure and harden later, and you're essentially wasting a lot of time and money. The reason that the focus is where it is right now on the IT side is because these plants, like I was saying before, are all really, really, really old plants. So you've got all these systems that are on a network that weren't even designed to talk on a network because they were built so long ago. And that's causing all kinds of headaches and flaws and vulnerabilities that really shouldn't be there. So we just sort of take for granted when we go out and buy new equipment that it's going to be better than the stuff that's out there, because how can it be any worse? It can't really. Unfortunately, that's not always the case. What we see happening a lot of times is that when you buy this new equipment and put it in, you're replacing an insecure network with another piece of equipment that's a really insecure network, but in a user-friendly way, in a way that my grandma could probably exploit. And the reason this is happening is because manufacturers are putting features into their equipment like for example relays or MCCs that you can reprogram or reconfigure using your iPhone wirelessly or over a Bluetooth connection, or a PLC that you can access over the web, and it's just got no password or no security whatsoever, and you can make changes to ladder logic and the state of the PLC. And all that stuff, if you think about it, is really good from a maintenance and operations point of view, because it makes it easy to operate. You don't have to lug a laptop around from device to device every time you want to program it. You just bring your iPhone or whatever around and do it right from there. But from a security point of view, the trade-off just doesn't make sense. So those are the kind of things, the low-hanging fruit that from our point of view, from a control systems point of view, we can take advantage of now, prevent ourselves a huge headache later, and 5-10 years down the road when we've replaced a lot of these systems, we don't want to run into that same problem again. Wade's going to talk to us a little bit about securing your plant and complying with some of the regulations that are out there.
Okay, how to meet compliance and protect your plant. This is all going to be fairly common sense to you folks, but to control system engineers, it's not so common sense. It's pretty new to us. Okay, so rules and regulations out there. Right now, NERC is a big one. They can impose fines of up to $1 million per day per violation. Some of these plants have hundreds of violations. It's geared largely toward protecting the grid as a whole. We also have NIST, which is the National Institute of Standards. These are all voluntary standards. It covers everything from cell phone use to implementing domains, etc. Finally, you have the NRC, which is the Nuclear Regulatory Commission. This is mandatory for all nuclear plants. Compliance is required to maintain your operating license. And they did just recently release new standards. Up until then, it was all physical security. There are many others. We talk about them in our paper. I'm not going to talk about them today. Okay, so real quickly, policies, lists, and procedures. We've seen a lot of organizations spend upwards of a year trying to determine how to arrange their new policies to meet these standards. Here it is. This is what we recommend. You need at least 3 lists. The first would be a sites list. Things like generating stations, backup control centers, distribution facilities. Then you have systems lists, which are internal to each site. So for a generating facility, you might have coal crushers, burner management, control room, etc. And then internal to each system, you'd have devices such as PLCs, DCSs, recorders, PCs, servers, etc. You don't want things like valves or solenoid valves or any of those components on there, because you really can't protect those devices effectively at all right now. You will need a set of master drawings, your network diagrams. A lot of organizations right now are just trying to create logical network diagrams to give a general idea of where they think a connection might be going. It's not a good idea from our perspective. You can't protect a plant unless you know where every connection and every port is. Okay, so the first procedure you need is policies. It gives a general overview of what compliance standards you have to meet, sets your roles and responsibilities, and gives a general overview of all the other procedures and whatnot. The last 5 are pretty self-explanatory: information protection, physical security plan, electronic security plan, and the 5th one is a pretty big one, so we do feel that one deserves its own procedure: change control and configuration management. You'll also need design guides. You shouldn't plan on these, you should just develop them as the need arises. But ultimately the goal of this is to design a set of policies that will be compliant with any standards that come out, even overlapping standards. Okay, so the first step of meeting compliance is to identify all your cyber assets, to classify them. Classifications are used to prioritize the devices. Ideally, they should be based on likeliness of attack, ease of attack, and importance to operation. You need to design a comprehensive, automated, and open-ended system. The only way to do this is to track your classifications in a database, to automate your classifications, and to do it in such a way that any new regulations, you don't have to modify your process very much. Categorization is largely focused on categorizing information as top secret, sensitive, etc. Okay, so electronic security controls, network electronic hardening. This is segmentation. This is protecting your network as a whole. First, you got to define a demilitarized zone. Any device that actually touches the outside world needs to be in the demilitarized zone, even if it's a relay or something very simple. After that, you have the primary electronic security perimeters, which is the entire network as a whole. Secondary electronic security perimeters would be a system or a device grouping, and tertiary ESPs would be something like a DCS cabinet 1. All ESPs need to be protected. All access points need to be protected effectively. Device electronic hardening, this is our definition. It took a long time to come up with. It's a lot of legal jargon. I'll just read it real quick. To ensure that only those ports, programs, and services required for normal and emergency operations are enabled, to ensure all security policies are met, and to add or strengthen security mechanisms to result in a more secure system than initial examination revealed. That's compliance for you. Have fun. Okay, so device electronic hardening generally involves these things. You've probably all heard about them. A lot of these keywords are new to control systems engineers. Anyway, you have to do surface area reduction, configuration, and security settings. You have to install protection software of some sort. You need to do communications hardening, limit the protocol use you use, encryption, authentication, etc. Data hardening, as well as hardware redundancy. Hardware redundancy is actually implemented fairly well right now. That's just the way we've been doing it for many years. You don't want an entire plant to be shut down because one computer crashed. Also, you have to account for maintenance. Okay, plant physical hardening. It's pretty much the same thing. You got to define a demilitarized zone. It's generally the area between the plant and the fence that surrounds the plant. You'll generally have 3 or 4 access points there. One for employees where they get in and out of the plant, another one for coal, another one for things like lime or ammonia. You've got to define a primary PSP, which is generally the building of the plant, and secondary PSPs are rooms. You also got to protect these using something, preferably 2-factor authentication. Here's another legal definition for you. I'm not going to bore you with it. I'm not going to read it, but this is the kind of stuff you got to deal with in compliance. You've got to define these things because the standards really don't tell you how to do it. Anyway, whatever definition you come up with for these things, you got to do it in a systematic way. Area physical hardening generally involves security devices, locks, keys, cameras, etc. Target hardening is focusing on a specific hardening to deter or delay an attack on a specific area. Materials hardening, like Paul said, there's a lot of dangerous chemicals, ammonia, coal, etc. Damage mitigation is things like installing blast walls. Access point management, we already talked about. Environmental hardening is inherent deterrents, such as lighting or shrubbery or installing roads in a certain way. Security personnel policies, patrols, how often you have to go on patrols, how often you got to store your tapes, and how long you got to keep them. And finally, you got to do something about social engineering mitigation. There's not much you can do about it. You can train on it, which they're kind of doing somewhat effectively right now, and you got to control communications, which is kind of limited. Okay, the last thing you got to do to meet compliance is incident response and as well as security reviews. We're not going to talk about that today, but here's a couple standards to get you started. Okay, so how do you protect your plant? The idea is pretty simple. To truly protect a plant, you've got to if you do it right, it doesn't matter what compliance standards you're required to meet. You'll be fine. Just do it right. Okay, our case study is security flaws and mitigation of a programmable logic controller.
Okay, before we start talking about security flaws and mitigation of the PLC, let's talk a little bit about some of the assumptions that were made. First of all controls are associated with the PLC. That means all the safeties, all the interlocks, everything is PLC controlled, all the electronic safety as well. Systems are simplified. We have to carry this thing over here, so we have to make it as small as possible. Only vital I/O is represented on our demonstration. Again, process and the logic knowledge has already been obtained. This means is that if you already hacked it, you have to know what the process is. I mean, just varying some variables really won't do anything. You have to know what the process is, and you have to know how to affect it at the right times. Again, these scenarios are conceivable for a percentage of plants, but you're not going to find this in every plant. But be sure there are as many problems as there are processes out there, potential problems. Talk a little about the hardware. We have a PLC of an undisclosed manufacturer. and model. Basically, PLCs came out at the end of the 1960s, beginning of 1970s. American automotive industry wanted to reduce the massive amounts of relay logic they used for the controlling of their installations, so developed the PLC. The network interface module that we have basically comes in two flavors, standard and web-enabled. The one we have basically takes the proprietary serial communication and converts it to proprietary Ethernet communication. Other devices that we have here in front of us, we have a variable frequency drive. I think it's this side right here. And we have underneath the board a three-phase motor with that spins the indicator of the wheel. Some other devices are the lights and the switches. Basically, lights present the outputs on by the PLC, and switches present the inputs. Paul, talk about security flaws.
All right, so the security flaws in this device. The PLC that we have here is something that is really common in the industry right now. We're not going to tell you which one it is, but it's something being used all over the world. We set it up and started playing around with it, and it took us only about 2 or 3 hours to find 3 horribly wrong security flaws with this device. The first one is that the device has a module in there, an internet interface module that lets you communicate between the PLC and a computer or an operator station using an Ethernet. The module it comes in 2 flavors. All right, there's a embedded web server on that module that lets you just type in the the IP address of the PLC and access the PLC over the web, essentially. The 2 flavors that the device comes in are a non-write enabled device, so a device that doesn't let you write back to the PLC. You can only read data from it, sort of see what's going on. That's the version that we have. There's the other version, which is a write-enabled device that lets you not only read what's going on in the PLC, but change registers and inputs and outputs so that you can affect the ladder logic and anything that's going on in the device, essentially. Probably a little bit less secure device, you would think. What it turns out is that both devices have the same functionality, apparently. When you go to the web page on the non-write-enabled device, the one that we have, it redirects you to a page that doesn't let you write stuff. If you open up the source code of that page, you can look at it and you can tell it's redirecting me this way. But if I go to this other page, I have access to all of the functionality to write to that device. So that's really dangerous because you have the device out there. Somebody thinks, okay, well, I can't write. Nobody can write to this device except through the proprietary software. So I'm safe. So I don't need to set passwords. I don't need to protect it. I'm fine. But that's not the case. They both have the exact same functionality. You can use that to exploit the system. The second flaw that we found is that by default, this thing is not password protected. And when I say not password protected, I don't mean the default password is admin or admin password. I mean they literally thought that password protection was not a feature that people would want to use by default. So it's just not on there. You can password protect it. So if a security-minded person is setting this thing up, they say, even though you can't write to the device, apparently, I'm going to still put a password in there. The password is enforced by a short JavaScript, which is run on the client's computer, meaning that anyone with a debugger, JavaScript debugger, so something like Google Chrome comes with it automatically, can go in there, look at the code, see what the variables are, see the password that the host is sending you, and you have the password right there. That's all it takes. But it gets even easier than that, if you can believe it. You can also just skip the password checking completely. All right, the web page works by sending commands back to the PLC to a CGI script. All right, so if you know the URL, you know the command you want to send, all you've got to do is send that command to the URL. It skips the password checking completely, making it completely pointless. It also doesn't do all the formatting checking and things like that are done on the web page too. So you have potential to do a buffer overflow or send any kind of garbage you want in there. There's nothing checking that stuff. So that's the third one is the one we're going to use right now. We're going to demonstrate a few common functions of a PLC and show you what happens if I'm over here with a script sending commands that I'm not supposed to be sending to the PLC and what the outcome of that's going to be. That is if the demo gods are in our favor. We have a lot of equipment up here, so there's a lot of things to go wrong.
All right, while Jay's setting that up, I'll tell you about this first demonstration. This is a demonstration of a single component, a VFD, which is a variable frequency drive. Mm-hmm. It controls both the speed and direction of a pump or a fan. Okay, so this is the graphics screen an operator would typically see. He has direct control over manually slowing down or speeding up this VFD. So Jay, go ahead and speed it up for us.
You guys can also see it turn here.
Should be turning there, hopefully. Speed it up one more time. All right, well, now we're just going to show that this exploit works. Paul, can you slow it down for us? And speed it up one more time for us. Now this is pretty dangerous. I mean, when you get direct control over a component as powerful as a VFD, you're directly controlling how much material is forwarded to some other area of the process, whether it be steam or coal or slurry or whatever. So both upstream and downstream components can be affected by this. This is a very dangerous situation. The second system we're going to simulate today is enunciators. Jay's going to get that set up for a second.
It might not work. I'm going to have to disconnect first.
All right.
Yep.
Good. Okay. Enunciators tell the plant operators of problems. They're kind of like alarms. Plants usually have a few alarms flashing all the time just due to maintenance activities or faulty equipment. They know about these. They know which ones are false, which ones are real. Physical enunciators usually accompany the software enunciators you see up here today. We're not going to simulate those because we don't have the hardware. But anyway.
We have to dump the program in and restart the application every time we do this, so that's why it's taking a little longer.
Yeah.
But we're almost there.
Variable frequency drive. What it does is it varies the frequency that's sent to a three-phase motor. It also varies the phase, which changes the direction. You vary the frequency to change the speed.
You gotta reconnect.
They're very common in the power industry. They're very powerful, very useful stuff. They can be. The model we have here does have a network connection. We're not using it today, though. Okay, so this is what you typically see on an operator screen. You see a few alarms flashing due to maintenance activities or whatnot. No big problems. And now we're going to show Paul has full control over the enunciator screens. All right, so Paul just said hi to the operators. Now you could do this, you could say hi or FU or whatever you want to the operators, but ultimately if this was a real attack, that wouldn't be the goal. The real goal would be to suppress the alarm so the operator can't see what you're doing in some other area of the system. This would cause more damage with your attack.
So just having control of the enunciator has control of the output, not the actual alarms going off. He's not causing the problem. He's just
No. He's just suppressing the operator from knowing about the problem. Yeah. It can, because sometimes these enunciators are controlled. The enunciators that are on the walls, they're controlled by lights in the back. They're often controlled by a PLC, just like we have here today. So if you get control of one, you get control of another.
Are the controls that difficult to read on a real screen, or is it just the projector?
It's probably just the projector, I'm sure.
They have to see the controls, otherwise they have trouble.
If I took and I started that cause on this system over here, that's going to redirect body, not suppress it, maybe do that.
Well, if you get
your attention to fixing what the hell is going on, right?
If they see something like that, they may just shut down, they may trip the whole plant. They may just stop the plant from operating because they have no idea what's going on. They no longer have control over the plant.
that would freak out an operator right there if we did
Yeah.
that.
Yeah, but I mean, I've got your attention focused there, just like Gallagher.
Sure. Okay, so the third system we're going to simulate real quickly is the bottom ash system. So what happens is you have a boiler, a burner, FD and ID fans, which are forced draft, which blow air into the furnace, and induced draft, which kind of suck out the smoke and the ash. You also have water tubes running down the side of the boiler and tubes hanging inside the boiler that all feed steam to the turbines. There's two types of ash. There's fly ash and bottom ash. We'll exploit the bottom ash system today. So I'll just give you a quick overview of how the system's supposed to work. The hopper's filling right now. That's what the green means. The fill valve up top is open. Now the drain valve opens, the hopper fill valve closes, the crushers crush the slag that's melting down the sides of the walls. Now the spray valve opens and sprays the little bit of extra stuff that's stuck to the walls, and the process starts over. It fills again, etc. Okay, so now you're going to see Paul exploit this system and cause a real mess.
Hold on a second.
Just a moment.
To get to zero. Go ahead.
Okay, so now Paul is setting the state back to 1. The fill valve is open, the drain valve is closed. You saw what's supposed to happen. The drain valve opened for a second and closed again. The fill valve open, and you're just filling that hopper all the way up. Eventually what's going to happen is water is going to get inside the boiler. You could put out the flame, possibly cause a boiler explosion, at least hypothetically. If you also have control over the enunciators, the operator might not know about this. If you have control over other systems, this might go completely undetected for, many, many minutes. And you could have a real mess that could take weeks or months to clean up, possibly fatalities.
You say a real mess takes weeks or months to clean up. What's the effect of that to the power grid?
It depends on the facility. It really does. If it's a 2 gigawatt plant, it could affect the grid as a whole. That's specifically what NERC compliance is focusing on, is protecting the grid as a whole. So if you generate, 2 gigawatts or more, you got to be concerned about that. It also depends on how quickly it happens. If it happens real quickly and you lose units completely and people are unaware of it for a little while, it could take out a lot of area.
If the plant is unique, each plant's designed on its own, you've got to do some serious discovery to understand what the PLC is doing.
Yes.
Absolutely.
Yes.
You're going to have to do some insider discovery to find out.
Right.
What this
A lot of this information is publicly available. A lot can be obtained via social engineering. You do need to know a little bit about the process. I mean, this is one thing we're trying to get across to you all today. It's kind of a new concept called malicious process design. Process design is something we do all the time, but designing it to be a dangerous process, sometimes it happens inadvertently. We're kind of afraid that it might happen intentionally in the future.
The other problem with that, to address your point, is if you were at the talk earlier, he talked a little bit about that, how you have to know both sides, not just how to get into the system, but what to do once you're in there. The problem is that, first of all, if you're already on the network, a lot of this stuff you can probably find on there, and there's all kinds of vulnerabilities. There was one released recently about Siemens about how you could get access to essentially the process map. So in addition to that, it could be there have been instances where ex-employees, I think there was one in Australia in a waste management plant, who already knew the entire system. It was a contractor who knew the system. It's not impossible to know the process, or if you don't know it, to get that information.
Right.
Yeah, way back there. Yeah, you.
Yeah, can each of those dangerous operations be triggered with like a single click or a single keystroke?
Unlikely, but possible. Different systems are designed differently. You have to understand there's like 5,000 power plants in the United States built between 1940 and a year ago. Whatever you do, it's going to have to be plant specific. It will always be plant specific. They're all just designed completely differently.
Quality assurance and independent verification and validation is done by who?
There are quality assurance engineers that do that. Nuclear is much better than fossil right now, but it's starting to get better.
Different organizations, those policies and procedures are separate and independent, or the boxes are
Sorry, I didn't hear you.
typically in an organization, those are independent, so that the box isn't watching the shipment.
Yes, that is true.
You didn't notice that in your organizational structure.
That's true. We should have put a QA in there. I guess in my experience, QA isn't always required for things like CT sites, combustion turbine, combined cycles, or even fossil plants. Yeah, we're trying to. Well, typically designers are separate. We design them, or we lay out the basics. They draw up the drawings. What's supposed to happen is supposed to go to a QA, but in a lot of organizations, QA is just like a mechanical engineer who's reviewing control system drawings, electrical drawings, civil drawings, etc. So, I mean, nuclear is much better at this than everybody else. You ready? I think at least one or two of them are already known about, and their response was to, make sure it's running on a secure network, to unload it on the client. Yes, sir.
What about vendor required backdoors? Specifically, certain turbine vendors require a connection into the turbine at all times to constantly tweak and keep the turbine at maximum efficiency.
I've heard of connections similar to that. I haven't heard of that one specifically.
That's completely true. I mean, a lot of times they require that you have that connection there for to maintain your warranty, so that they can monitor the operation of the turbine and make sure you're not doing something that's going to void the warranty. And that's definitely a vulnerability that could potentially be exploited. It's something that a lot of times doesn't even go through a DMZ. It's just a connection straight to a vendor.
Correct.
Mm-hmm.
Yes, sir.
At the NSA, you can't use a coffee maker, a blender, even a cat box unless it has common criteria testing. Basically, everything has to be validated to be used in any kind of a secure environment.
Right.
Would it make sense to have something in basically the same type of common criteria for any system that's going to support any part of the grid?
Agreed. Nuclear already does that. They're really strict about this stuff.
With fossil, all of that stuff is privately owned, so to be able to get agreement on that kind of stuff is it's an undertaking.
That's what these standards are trying to do. The problem is there's so many different standards spread out, different organizations. Sometimes they overlap, and you don't know which one you have to comply with the most. It's a real mess right now in terms of the standards that people are trying to comply with, and also there's a lot of resistance. People don't want to change. It's also very tough for a plant that was built 50 years ago that was modified slowly, decade after decade.
I mean, there is a lot of healthcare systems, information systems they have. I'm not sure what they come under, but they go through pretty rigorous testing. It seems like a lot of this has already been done, trailblazed before, and whether it takes regulation or something like that, it shouldn't be that hard to bring it to the non-nuclear side.
I agree. The problem is one of the points Paul made is it's bad design. I mean, these PLCs just simply were not designed with security in mind. They were designed to get out quickly as possible, to make the most profit, and to give functionality, good functionality. And they do that well. But in terms of security, there is none.
I understand it's a complicated system and there's a full need for a local area network, but I'm really not sure why there needs to be a connection out to off-site. Basically, you have a self-contained plant, does everything it needs to do, and you do have less need for that individual password. It seems like you shoot yourself in the foot if you don't have an air gap.
Well, there is somewhat a need. You've got so many power plants generating so much electricity, each with a different amount. Then you've got renewable sources coming in now. And when you look at the graph of how much energy we consume in a day, it's like this. It's up and down. So that all needs to be coordinated. How many megawatts is each plant generating? Which units go up? Which ones get priority? I agree. If there's a way we can do it without having a connection to the outside world, we should. I don't think we've determined how to do that effectively yet. I mean, even in the olden days, I think they used telephones or something, But, yes, sir.
I was in a skating class with someone that worked at a
the power grid. And what they said is that between their SCADA networks and their business networks, they had two one-way systems. So data came in on one connection and out on another. Is that common to at least, even if you've got that connection, provide that kind of separation and granularity? Or are we just throwing a TCP connection up, straight line TCP connection, firewall if we thought about it?
Right now, my impression is that most of them are just straight TCP connections. A lot of them are trying to start to put in things like data diodes, and that is a good, effective thing to put in. It's not enough. It's a start, I guess. Yes, sir.
I know in a lot of industries, they have either safety integrated systems or mechanical fail-safes, even if you show the HMI, you're still not going to talk.
Right. No, that's true. There are always mechanical interlocks. The problem is older plants weren't built to modern standards. Also, if you have a 50-year-old plant, sometimes these mechanical interlocks go uninspected for years or decades. For example, pressure safety valves, which are set to explode when the pressure gets too high. If they get rusted, they're very sensitive components. If they get rusted, they're going to fail.
The good news now is we're concentrating on control systems. The safety integrated systems are now moving to the IT standards as well, so they're starting to under IP.
Yeah.
The exposed when previously weren't.
Even if you have mechanical interlocks, I mean, there's still a danger here. If you put hello up on the operator's screen and his alarms, they're going to shut down the plant, and that thing takes a day at least to start back up again. So I mean, that's wasted revenue, wasted time, and then there's you're probably going to get fined. You probably got to go back and re-examine your network. So it's a huge waste of time. Just do it right the first time, and you don't even have to worry about your mechanical interlocks being safe. They're doing what they're supposed to do.
Any other questions? Yes, ma'am. It was in there a little bit further back. That's true. That's another point we're trying to make today is you don't need a cyber attack to have a real incident on your hands. I mean, look at the Deepwater Horizon. I mean, it's terrible. That's true. An insider could use the knowledge, disgruntled employees or just oblivious employees who don't know what they're doing. Training is key. But you're right. I mean, there needs to be more safety systems inherently designed in these processes, and they need to be maintained. And I don't think we're doing an effective job at the moment. Yes. On the what?
Hey, Wade, do you want to wrap up and we can have people come up and...
Okay, yeah, we're going to wrap up real quick and have a QA session. I think it's it's right over there somewhere.
Let's just do it. We can do it in here.
We can?
That's what he said. There's no one else in here, so yeah, we can stay in here.
Okay. More questions? We'll
stay in here. If you've got a laptop and you want to try connecting to the PLC and do whatever you want to it, you're welcome to try.
Yeah. So we do have a solution to these security flaws we found. It's called the Tofino Security Compliance. It's like a 2-port managed Ethernet switch. It's got firewall protection. It's got a little bit of intrusion detection prevention as well as alarming. It's designed by control system engineers for power plants and industrial facilities. If you want to put this device to the test and prove it works for us, we'd appreciate it. I don't know if you guys can actually hack the network through it. We'll see. Welcome to try.